Hello pre-calculus students, here with our first section of the derivative and the derivative of the tangent line. Before we get into some of the notation and so forth, let's just take a little stroll through memory lane. And remember how you talked about tangent lines before? That was to circles. Now for a tangent line to a circle, it crosses a circle at exactly one point. So if I want to have the tangent line to the circle at point C here, the first key thing is to come up with a radius. And if I make that radius segment from here to here, now I can just go perpendicular to that radius. So now I go for perpendicular line through this point, perpendicular to this line, and there's your tangent line. So easy peasy coming up with a tangent line to a circle. Okay, hits the circle in exactly one point. All right. The thing is though, what happens if we try and do the tangent line to a curve? It's a little trickier because there's no one center of a curve, like in this case a parabola. So we can't just come from the center of the parabola and go perpendicular to that. What we have to do is look at the secant line first, and that's what I'm doing here. I've got a fixed point here at 1, 1, that's A. And I'm going to move this other point around B, and I'll form a bunch of secant lines. Now none of these lines really represent how fast the function's changing right at 1, 2. To turn the secant line into a tangent line, what we have to do is let this gap between the 2 points, A and B, go to 0. Have B become A. So the secant line turns into a tangent line right there. Now, right there it disappears because technically it's undefined because I'm trying to subtract 0 over 0, and that's not a slope. Now, the GeoGebra knows how to do this. Let's just slide this over here for a second. You can actually ask it, come up with a tangent line, tangents, select a point or line, then a circle, conic, or function. So I select this point, I select this line, there's your tangent line of 2x minus 1, right there. And it has a slope of 2. And sure enough, as I move this thing along, let's change this line into equation form like that. As I move this secant line along, let's go to the grabber again, the secant line slowly becomes the tangent line. And right there, as we get closer and closer and closer, see it's got 1.9, x minus 0.9, 1.92, 2.04. See, it gets really close. When I try and get too close, though, it just becomes undefined. So it's a limit process that we're going to be looking at. Okay, now let's investigate that limit process with our notes. Here are in your 18.1 notes, the derivative and the tangent line. So first we're looking at 2 points on a function, x1, y1, or x1, f of x1. So you can think of those as 2 points. 2 points, and you got x1, comma, f of x1, and x2, comma, f of x2. It's just sort of functional notation for 2 points. So here's the slope of the line between those 2 points. And the line we're talking about now is, let's get our line drawer here, is this line between these two like this. That's a secant line. And it's also called the average rate of change. Average rate of change, ARC, is equal to the slope of the secant line. Okay? Now, let's contrast that, though, with what happens when we want to try and come up with the slope of the tangent line. To get the slope of the tangent line, we've got to have x2 turn into x1, have the 2 points become 1. But the classic problem is you get 0 over 0, like we saw in GeoGebra. It's undefined. So we want to somehow come up with this tangent line. Let me draw you a tangent line in here. The tangent line is going to be like this. There's a tangent line. See how it's different than the secant line? And it's defined as the instantaneous rate of change of f of x. And it's the limit as h goes to 0 of f of x plus h minus fx over h. Now what we do is kind of reassign here. Instead of saying x2 and x1, we're going to use f of x plus h and h. That is, we're going to figure out how much over we're going here. H is the gap between the 2 points. It simplifies the algebra a lot if we do it in this format. Now, the instantaneous rate, IRC is the instantaneous rate of change. It equals the slope of the tangent line, and it is our derivative. And that's what derivatives are all about. Now let's try applying this definition to f of x equals 5x minus 4. So the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. And now you can see why this is in this simplifying this difference quotient. That's what it's called, difference quotient, because it's a quotient of two differences. H actually represents a difference, the gap between the x-coordinates of these 2 points. Watch out substituting in here. F of x plus h, you put the x plus h in for x. So it's 5 times x plus h minus 4. All of that is f of x plus h, minus f of x, which is 5x minus 4, all over h. So we get the limit as h goes to 0 of 5x plus 5h. Got an extra x in there, sorry. 5x plus 5h minus 4 minus 5x plus 4 all over h. And so that's the limit as h goes to 0 of the 5x's cancel. The negative 4 and 4 cancels. And we get the limit of 5h over h, or the limit as h goes to 0 of 5, which is equal to 5. So f prime of x is equal to 5. And that's saying basically the slope of the tangent line for a line like 5x minus 4 is always going to be 5, because this line is constant slope. Now I want to do another example here, though, of let's crank it up to a more difficult function. Let's say f of x equals 1 minus x squared. So now the derivative is f of x plus h minus f of x all over h. I'm forgetting something key here. Remember what that was? The limit as h goes to 0. The limit as h goes to 0. If you don't do that, it's wrong, because now you're just finding the slope of the secant line. The tangent line is gotten by looking at this limit process. So 1 minus x plus h squared minus f of x, which is 1 minus x squared. So all this is in a big group. That's f of x plus h. This is f of x all over h. So the limit as h goes to 0 of 1 minus x squared plus 2xh plus h squared minus 1 plus x squared all over h. We see some stuff is canceling already. And now let's continue our limit. The limit as h goes to 0. Let's keep expanding here. Negative x squared minus 2xh minus h squared plus x squared all over h. And again, we see stuff canceling. So we have the limit. Oops, see how to get the time there. The limit as h goes to 0 of negative 2xh minus h squared over h. At this point, some students like to actually factor out the h. Negative 2x minus h all over h, and then they can cancel the h's, or they divide the h into both terms. In either case, you end up with a limit as h goes to 0 of negative 2x minus h. Now when you evaluate the limit and put in 0 for h, you get negative 2x. So there you go. When f of x was equal to 1 minus x squared, the derivative was negative 2x. Now, there's an alternative definition which goes back to our original difference quotient concept. There's the difference, and it's a quotient of differences, DQ, difference quotient. And the alternative definition is sometimes handy if you'd rather factor with a binomial underneath. Sometimes you don't want to do it that way, but sometimes you can. So just be aware of this alternative definition. We're going to try it on this one right now. The alternative definition says we're going to find f prime of, let's say, some c by looking at f of x minus f of c, the limit as x goes to c of f of x minus f of c all over x minus c. So it's a limit as x goes to c of x squared minus 5x plus 6 minus f of c, which is c squared minus 5c plus 6 all over x minus c. So it's a limit as x goes to c of x squared minus 5x plus 6 minus c squared plus 5c minus 6 all over x minus c. And we see some things canceling. Let's see. The 6 and negative 6 cancel. That's it. Now here's where the factoring gets a little trickier. That's why this form is not as preferred, but in some cases it does end up being a simpler approach. So we've got the limit as x goes to c. Now I'm going to group it like this as x squared minus c squared minus 5x plus 5c all over x minus c. And I'm going to try and factor out an x minus c. I can factor the first part in x minus c times x plus c. And I can factor this part. I can take a minus 5 out, leaving behind x minus c all over x minus c. So it's a limit as x goes to c of x minus c. Yeah, let's get that cleared up. X minus c times the big quantity x plus c minus 5 all over x minus c. Now we can see that factor cancels out. And that's what was creating your 0 over 0. Now when you look at the limit as x goes to c of x plus c minus 5, you get c plus c minus 5, or 2c minus 5. So f prime of c is 2c minus 5. Now some people are bothered by the fact that you end up with an answer in c. Well, you can just easily change that around. So basically we started with f of x equals, I believe it was x squared minus 5x plus 6. And we end up with a derivative of 2x minus 5. I think you got to start seeing how there might be some shortcuts to just eyeballing a derivative right away. And we'll talk about that in the next section. Now, differentiability of function means you can take its derivative. You're able to figure out f prime at x. The slope of the tangent line exists, and there is a tangent line. And it's defined as differentiable. And if it's differentiable, it means continuity. Differentiability, D implies C. If f is differentiable, then f is continuous at, let's say, x equals c. If f is differentiable at x equals c, then f is continuous at x equals c. Differentiability implies continuity. That's the mantra we're talking about. Differentiability implies continuity. Basically, differentiable means that it's smooth. And when we look at x to the 2/3, you look at the graph, look at what's going on right there. You got a sharp corner. So this is not differentiable at x equals 0. It's got this sharp corner because you can't really draw a tangent line. The tangent line from this direction looks one way, the tangent line looks the other way. In fact, we're going to use our derivative rules next to show that if f of x equals x to the 2/3, the derivative is 2/3 x to the negative 1/3, or 2 over 3 x cubed root of x. And basically when x equals 0, then we have an undefined derivative. So not only is that a sharp corner, the derivatives approach verticality there from both directions. Now what if a function is not continuous at a point? Is it differentiable there? So imagine I draw a function like this. Let's get some axes on here. And then let's draw on our function and say the function looks like this. So the function is defined everywhere. Is it differentiable there? And the answer, no. Is it differentiable there? No. If it's not continuous at the point, you can't possibly draw a tangent line that'll satisfy both directions. So if it's not differentiable, then not continuous. And this follows for some of the things you studied in geometry. Remember that in geometry last year? The implications. Differentiability implies continuity. And if it's not continuous, it's not differentiable. Remember those called from logic? The contrapositive. And I didn't put enough blanks in there. Contrapositive. Here's some of the notation you should be familiar with. I've been using this prime a lot to represent the derivative, but you can say dy over dx. This is kind of the idea of the difference quotient taken to the extreme. That d stands for the differential, the infinitesimally small change in y over the infinitesimally small change in x. And there's various variations on it. There's your y prime. You can use a big D too. But notice a lot of these other notations specify what the dependent variable is and what the independent variable is. Okay, flange out.